Okay, so let's move on to our next model that we're going to look at today, and that's going to be a PC enclosure, and this is going to be an internal flow analysis, and we're going to be using the capabilities of our electronics cooling module. So electronics and LEDs are very common applications for flow analysis. Basically, electronic components don't work properly if you can't manage the heat. And we've got tools within flow simulation that allow us to more accurately model our electronic systems. So if we display all our callouts in this particular model, it's a little bit more going on here than in the prior couple models that we looked at. And we have our 2 resistor components, which is actually a JADEC standard for modeling microchips. And so that's what all these small callouts are, pointing to our electronic components. We also have an external fan defined that's pulling the air over the heat sink. The heat is getting to the heat sink via 2 heat pipes, which are included in the electronics module capabilities. And then as we scroll down, we'll see that there is a printed circuit board in the model. And if I edit the definition here, this is part of our engineering database and part of the electronics cooling module. And what this does is it enables us to define a circuit board as a lumped thermal mass, because we wouldn't want to get in and try to mesh really small, thin layers of copper. So we can say how many conducting layers are in the model, the percent of coverage of each of those layers, and that layer thickness. And then SolidWorks will automatically calculate the equivalent thermal properties of that PC board, so we get a more accurate representation without trying to model the minutia of tiny layers of copper. The 2 resistor components, and the reason that we have this type of capability is that we want to be able to evaluate our junction and case temperatures. And if you look at the a material or a spec sheet for electronic components, those packages will have case and junction thermal resistances. And then we can enter those along with the package size into the definition of our different types of packages. So we have, with the electronics module, we get a whole array of different types of microchip packaging so that we can evaluate the junction and the case temperatures, which we're going to be concerned with. So the goals of this particular simulation are to monitor the temperatures of the case and the junction of the CPU. And we created surface goals before, and these are a volume goal. So we're looking at the average temperature of the case and junction bodies of the CPU. And, simulation without comparative analysis is kind of pointless. So in this case, we have one flow project here, but we have 2 different levels of power on the CPU, and we want to see how that is affecting those temperatures and whether we need to add more flow, a bigger fan, or a larger heat sink. Let's start with our flow trajectories. So we see the fan is pulling the air over the heat sink, and it is entering the model from our perforated plates, or an idealized perforated plate. So where we have pressure openings for this model, we also have a restriction based on a perforated plate model, which is kind of similar to the PC board, meaning, we don't want to mesh in a lot of detail, but we do want to have a pressure restriction that represents what's going on in reality. So we have a perforated plate model on the bottom and one on the side where the air is coming in, and it's being pulled out by our fan. And if you zoom in real closely, these vectors are representing temperature right now, and we see that we're picking up the heat as we move across our heat sink, as we would expect. And this can be useful information to look at when you're designing heat sinks, for natural convection versus forced convection models. And in this case, we might even be able to go a little bit finer with our heat sinks if we wanted to, because this is forced convection. And let's inspect the temperature of our CPU right now. So we can probe while we have our surface plot up. And by inspection, the top surface of the CPU is about 77, 78 degrees Celsius. And let's look at that with respect to a goal plot, where we can select our average and max temperatures. And yeah, we're right around 80 degrees Celsius for our maximum value. And it's pretty uniform temperature across the chip. Now we have the same version of this model, except the only difference is that if we go into our high power version, and we just look at the definition of our CPU, we're using the same 2 resistor model, except now we're working with 24 watts. So we want to see the effect on both the CPU temps and the adjacent chips in the model. So I can just go to my goal plot, say I want the CPU, and then I can also pick the chipset right next to it, add this to my goal plot, and we can do a comparison. So we have a nice summary table, and our CPU, obviously, because that's where the heat is being generated, pretty massive temperature delta. The adjacent components are seeing a 10 degree Celsius delta, and depending on our chip spec sheets, we might need to look into more cooling, or maybe select a higher volume fan or a different style heat sink. And if we want to pick a new fan, for example, we can go into our engineering database, and our fans are just defined by picking the face. This is an external outlet fan. And then with the electronics cooling modules, we give you all kinds of default fans in our engineering database, so you don't need to spend time entering in your performance curves for your fans. Those are already included with the electronics cooling module. Okay, so I'll stop and take a look at the chat panel And, oh, there we go. Yeah, sorry, I'm watching the chat panel, not the Q&A. Me bad. Yeah, the comparative is new for 2013, and yeah, it's a very nice feature to have. You know, Flow is all about doing multiple iterations, and it's a whole lot easier to compare them now. Okay. So with that, I'm going to jump out of the thermal and wrap things up with a little flow structural combo. And we're coming up on the hour almost. So let's shut our PC down.